Okay, so today we're going to talk about the relative power of synchronization operations. And I think this is kind of one of the most interesting lectures in some ways because of some of the things that we're going to discover here. In some ways, all the other things we've been doing in the course have led to this. So in the last lecture, we looked at shared memory computability. And we had we're looking at a mathematical model of concurrent computation and what is and is not concurrently computable. And we haven't really worried about efficiency. What we want to do is we want to write weight-free implementations. So every method call completes in a finite number of steps. This implies no mutual exclusion because mutual exclusion could be something that, if somebody's in a critical section and they stop executing, then no other method is going to complete. So we talked about the weakest register, which was a safe Boolean register with a single reader and a single writer. And we went all the way to atomic snapshots. And the rationale for weight freedom is we want atomic registers to implement mutual exclusion. So we couldn't use mutual exclusion to implement atomic registers. But what is the basic problem with mutual exclusion? So you have these three CPUs running along, and we have asynchronous interrupts, and one swaps out and suddenly becomes slower while the other two are trying to run faster. But the first one is holding a lock, and so the other two can't make progress. So there's no fault tolerance there. And Jean Amdahl's law will mean that you're spending time doing nothing, which means you're going to not get the speed up that you want. So weight-free synchronization might be a good idea in principle, but how do you do it systematically, correctly, or efficiently? So let's look at our old friend, the FIFO-Q. We have an NQ method and a DQ method. And when we have two threads, we have a weight-free queue that we can implement that looks something like this. I think it needs to have some checks on the bounds for the head and tail to make sure that you don't write too many things or read too many things. No, actually, no, it doesn't. It's got those while loops in there to do that. One thing that might improve this code, does anybody have an idea for something to improve this code? So let's look at the while loop in particular. Does anybody think that having an empty curly brackets there is going to be the most efficient thing?
Nope.
What should I put there?
You could put a condition variable instead.
Well, a condition variable is a bit heavier duty. We don't have any mutexes, right? And we don't have any condition variables. And the beauty of the two-thread weight-free queue is it's weight-free, right? So condition variables implies mutexes, and mutexes implies not weight-free. So what you're saying makes sense in the sense that in the context of chapter 8, but this is the goal here is to be weight-free. Any other thoughts about what might go in the curly brackets? Okay, so what I would suggest is thread.yield. Okay, so what's going to happen is the Java virtual machine has no idea that the real purpose of that loop is to wait for something. And so it's not going to, if that thread is, so the way execution works on a machine is you have however many user level threads mapped to however many machine level threads. Usually there's more user level than machine level. So what it does is it swaps what it's executing on. And it does it very rapidly. You don't normally notice it. but this while loop is just going to keep running. So as long as the current this current thread is in memory, right, it's just going to keep executing that while loop, and it's not going to succeed. So what we want to do is we want to tell the processor, hey, swap out, give somebody else a turn to change the state. So if we put a thread.yield inside that curly bracket, it should be a little better. Anybody have a question about that? Okay. We will proceed then. So what if we have multiple dequeuers? That same lock-free thing is not going to work. And so the grand challenge is to implement a FIFO queue that is weight-free, linearizable, from atomic read-write registers, and has multiple dequeuers. This is the new aspect. If I don't include that last aspect, the code on the last slide will work, right? So while you're thinking about that grand challenge, we will give you another puzzle to think about called consensus, and this will be important. So consensus works like this. Each thread has a private input. They communicate, and then they agree on one thread's input. Okay, and formally, to be consistent, all threads decide the same value, and the common decision value is one of the thread's input. Okay, but there is, and we're going to say that there's no weight-free implementation of consensus using registers. So this is an important thing to pay attention to, is the weight-free implementation, right? It's possible to make all kinds of, deadlock-free or starvation-free implementations of consensus, but we can't make, well, we can't make weight-free. We're going to show why that's true. So formally, there's this theorem by these three authors that says there is no weight-free implementation of n-thread consensus where n is greater than 1 from read-write registers. And the implication is that asynchronous computability is fundamentally different from Turing computability. Now, there is no formal definition of a parallel Turing machine. That is not something that the community has found to be particularly useful. But there is something special going on here nonetheless. So what we're going to do is we're going to try to prove this claim, and we're going to do that by assuming otherwise, and then we're going to reason about the properties of any protocol based on atomic read-write memory that could implement this consensus, and then we're going to derive a contradiction, and that will be our proof. And we're going to stick to binary consensus and n equal 2, because if we can't do that, then we certainly can't do anything harder. So the way it's going to work is like this. We have a weight-free computation, and thread A is going to move, or thread B is going to move. And a move means reading or writing a register, because that's all you can do with atomic registers, is you can read them and you can write them. Okay? And the two-move tree is going to look like this. So one thread A moves with a blue arrow, thread B moves with a red arrow. And we start with some initial state, and we're going to reach some final state. Okay, and it's got to be a finite number of moves, because that's what weight-free is. So we can draw it as a tree like this. And we're going to say a state is bivalent if, starting from that state, we can reach either 1 or 0. And we're going to say it's univalent we're going to say that a calculation is univalent if starting from one of these nodes in the tree, we can only reach a 0 or only reach a 1. So if I start here, right? If I start at this green arrow, at this green box, I can only reach a 0. And if I start at this other green box, sorry about the sloppy drawing, but I have to use a trackpad today. I can only reach the 1. Okay, so that's a univalent state. Okay. Any questions? All right. So this is what we call a one-valent state, because from this state we can only, whether we move with thread B or thread A, we can only reach a 1. So the summary is that a weight-free computation is a tree, and there are bivalent system states where the outcome is not fixed, and there are univalent states where the outcome is fixed. Okay, and since this is a binary tree, we have only one valent and 0 valent states, which are our 2 outputs. Okay, so the claim is that some initial state is bivalent, and the outcome depends on chance or the whim of the scheduler or whatever, and the multiprocessor gods do play dice. So let's prove this. Okay, so if in univalent, all executions must decide 0. Okay, including the solo execution by A, and in one valent execution, we must decide 1. With both inputs as 1, all executions must decide 1, and also the solo execution by B has to come up with 1. Okay. So what if the inputs differ? Okay, so if they're the same, that's easy. But what if they differ? Okay, so a possible execution includes solo execution by A that decides 0, and the solo execution by B that includes 1. Okay? So we have to make sure that we can do all these things in order to solve consensus. So we have to go from so there must be some critical state at some point in this execution. And when we're at that critical state, whatever we do, we're going to go to a univalent state, whether it be 0 or 1. And then and it's called critical because no matter what we do after this state, okay, we're no longer we're no longer bivalent. Okay, so from a critical state, we can go to 0 valent or 1 valent, depending on whether A or B goes first. And we can also reach a critical station. We can also have a critical state if only one side is 1 valent. So we could have critical B, which if B moves first, then we're in a univalent state. But if A moves first, we're not. And so we can have critical A and critical B, or simply C for critical. Are there any questions?
Yeah, I have a quick question.
Yeah.
Can you just briefly re-explain what valent means in this situation? Like, I'm just a little confused.
Okay, so bivalent means that valent is the number of states we have, right? So bivalent means we have 2 states open to us, and this is a problem where we're trying to solve binary consensus, where we have 2 threads, and each of them are proposing a value, and that value is 0 or 1. Mm-hmm. And in the case that we have both threads proposing a different value, we have to somehow arrive at a consensus. One of those values has to win, and both threads have to agree that that value wins. Okay, so if we start with a bivalent state, we're not sure what the outcome is. We're searching for a way to a weight-free implementation that gets us to that 1 or 0. Do you follow?
Yeah, that makes sense.
Okay, and the claim is that we're going to fail. So this is what we're trying to prove here, is that we can't make a weight-free consensus protocol with atomic memory. We're going to show that atomic memory just is limited, okay, in what it can do. So we're starting from a bivalent initial state, and the protocol, in theory, can reach a critical state. Otherwise, we would stay in the bivalent state forever, and the protocol would not be weight-free. So far, this is memory independent. It's true for registers and message passing and carrier pigeons and anything that just has read-write. So now we're going to talk about read-write memory to reads and or writes to same or different registers. And to complete the proof, we're going to look at executions that start from a critical state and threads cause the state to become univalent by reading or writing to the same or different registers. And we're going to end within a finite number of steps deciding either 0 or 1. And we're going to show that this leads to a contradiction. So here are the possible things we can do. We can read X, we can write X, we can read Y, we can write Y. And we can do it with thread A, which is blue, or thread B, which is red. Okay, so X.read in the blue is B reads X, or B reads Y. Okay. So we're going to start in a critical state. We're going to look at a critical state, and the A runs solo, say, and eventually decides 0, or B reads X or Y, whichever, and then A runs solo and eventually decides 1. Okay, and the problem is these states are going to look the same to A. I mean, the fact that B read something isn't going to make a difference to A, right? It can't come up with a different execution based on whether B read X or Y. So this doesn't really make sense. So what we're going to do is we're going to immediately identify the read option as not working. So now we're going to write distinct registers. So A is going to write Y, and B is going to write X, and we're going to decide 0. Then B, we're also going to consider B writes X, then A writes Y, and decides 1. And the problem is that we can't tell who won. We can't really tell, when A reads a 1 in X, I'm sorry, if A reads a 0 in X, it doesn't know whether B moved first or not, and vice versa. If you see a 0 and a 1 written here, you don't know what happened. Now, if A were to write 1, were to write 1 and to see that B hadn't written anything, then we would know that we won. But in the case that both write, we just don't know. So it's impossible for us to tell based on these writing to distinct registers, which leads to a contradiction. And so we put in 2 more nodes on our chart. And then there's the possibility that we write to the same register. But now we're back to the problem we had before, and that A can't tell if B wrote or not because it overwrote whatever B did. And so this doesn't work either. And so now we've filled up our chart with no's, which means we can't do this. We can't start with atomic read-write memory and build a weight-free consensus for a binary weight-free consensus. So a recap would say that atomic registers can't do consensus. If the protocol exists, it has a bivalent initial state, which leads to a critical state. And what's up with the critical state is we do a case analysis for each pair of methods. Whether we do reads or writes, no matter what we do, it all leads to a contradiction. So here's a question for you, and I need you to put on your thinking caps, all right? Thread A writes a value plus a timestamp in register R1, and thread B writes a value plus a timestamp in register 2. And each thread reads R1 and R2, and they use either the only non-blank register or the earliest one that's written. Does that work or does it not work? I want to leave you to ponder that one. And if you think of anything, I want you to speak up. All right, what does consensus have to do with concurrent objects? Okay, so let's say that we have, we're going to define an interface called consensus, and it's going to take an object and it's going to return an object. And we only consider one-time objects, so this thing's only usable once. And we want this to be linearizable to a sequential consensus object in which the thread whose input was decided on completed its first method first. That's method first. So we're going to define consensus as an abstract class, and we're going to implement some methods and leave you to do the rest. So let's consider this consensus protocol class, this abstract class. It's going to implement consensus, right? And it's going to have an array of objects that are proposed, where n is the number of threads, and it's going to have a private propose method, and that's going to take a value, and we're going to assign a value to that array. Actually, I think this is an error, right? So if you wanted to take this class and implement it and use the propose method for anything, you wouldn't be able to, right? Why is that?
If the processor stops working, then wouldn't everything it have done just not exist, really? Like if you're trying to do consensus?
So the propose method is going to be called probably before we call the decide method. And if you didn't ever call the decide method, then it would get lost. But I know that you're a C++ guy, Chris, and this is more of a Java question than a parallel programming question. That's a hint. By the way, I'm screen sharing. You all see the generic consensus protocol slide as my screen share, right?
Yeah, with the code.
Okay, now here's a question. I'm just questioning what exactly I'm sharing. Do you see anything over top of that screen now?
Yeah.
Okay, so I'm sharing my whole screen. I just wanted to, I couldn't remember what I had done, and I just wanted to make sure I knew. All right. The problem is the keyword private, right? If you subclass, you can't access private methods. What you normally want in that case is protected. So we have each thread's proposed value, and we have a proposed method, and then we have a decide. And we're going to, and that's going to do the heavy lifting. So here's a question. Can a FIFO queue implement consensus? All right, and this is what we're going to, the way we're going to make it work. So we're going to have the proposed array consist of two values, and in the queue we're going to have a red and a black. Okay, and what's going to happen is we're going to each of the threads is going to get an item from the queue, and it's going to get either the red or the black ball, depending on who moves first, right? So in this case, blue got the coveted red ball, so it will decide on the value. Alternatively, since red got the dreaded black ball, it will decide the other's value must be the correct one. And so we can implement our queue consensus protocol. In the constructor, we initialize the queue, and then we first call the propose method, which we couldn't do if it was private, but we call the propose method, and then we dequeue it. Okay, and if the ball is red, then we return our value, and if it's not, we return the other value, which is 1 minus I, or which is either 0 or 1. Okay. And that means the other thread won. Does that make sense? Anybody have a question about that? So to recap, right, we're trying to make a two-thread consensus protocol, and we're showing that given this queue consensus interface, this queue consensus class, we can implement the consensus interface and create a weight-free algorithm to implement the protocol. Now it's only weight-free because we assume that the queue, NQ, and DQ methods, or the queue DQ method is weight-free. Okay. So why does this work? So if one thread gets the black ball, then the other gets, if one thread gets the red ball, the other gets the black, and the winner decides her own value, and the loser can find the winner's value in an array, because threads write array before dequeuing from the queue. So we can solve two-thread consensus using only a two-dequeuer queue and some atomic registers. Implications: a consensus protocol from queue and registers exists. Assume there exists a queue implementation from atomic registers. Substitution yields a wait-free consensus protocol from atomic registers, which is a contradiction. We know we can't do that. Therefore, it is impossible to implement a two-dequeuer wait-free FIFO queue from read-write memory. So let's think about consensus numbers. We want to say an object has a consensus number n if it can be used to solve n-thread consensus, okay? And that means we can take any number of instances of x and together with an atomic read-write registers and implement an n-thread consensus, but not n plus one thread consensus. So this is going to determine whether we have, n thread, how many thread consensus we can build and what a consensus number means.
I think I may have missed this, but what is the n plus one thread consensus? Like, what's the difference between that and n thread?
Well, we implemented a two-thread consensus with our queue, right?
Yeah.
But we did not implement the three-thread consensus. Okay, so what we're saying is, we've shown that queue can build a two-thread consensus, but we can't build a three-thread consensus that way. It's a consensus 2 protocol. That queue is a consensus 2 operation. Does that make sense?
Yeah.
Now, you haven't tried to make a three-thread consensus out of that, and that isn't something that we're going to do in the slides, but we're going to talk a bit more about how these things, about n-thread consensus in a little more detail in just a minute. All right, so consensus numbers. So we have read-write registers have consensus number 1. That is, they can only solve consensus for one thread, which is utterly trivial, right? And a multi-dequeuer FIFO queues have consensus number at least 2. We haven't ruled out 3, but it's at least 2. Consensus numbers measure synchronization power. So if you can implement X from Y and X has consensus number C, then Y has consensus number at least C. And conversely, if X has consensus number C and Y has consensus number D less than C, there is no way to construct a wait-free implementation of X by Y. So this theorem will be useful and will have some practical implications. All right, so earlier grand challenge, we said snapshot means write any array element and read multiple array elements atomically. What about write multiple array elements atomically and scan any array elements? Call this problem multiple assignment instead of multiple write, or multiple read rather, or snapshot. And the multiple assignment theorem is that atomic registers cannot implement multiple assignments. And does that seem weird or what? Because a single location write, multi-location read is okay. Not a multi-location write, multi-location read. So we're going to prove that. And what we're going to do is we're going to write to 2 out of 3 elements of an array. And then we're going to show that that solves two-thread consensus. And that means it's impossible with atomic registers. And therefore, we cannot implement multiple assignment with atomic registers. So let's imagine that we have a 3-element array and that A writes atomically to slots 0 and 1. At the same time, B tries to write atomically to slots 1 and 2. And then any thread scan any set of locations. So the double assignment is going to work like this. We're going to have an atomic I1, V1, I2, V2. Okay, and that will atomically assign array elements I1 and I2 with V1 and V2. And then we're going to read the ith value with this read method. Okay, and so initially we have this green trying to write to these two locations in memory, and blue is trying to write to these two. And thread A wins if thread B didn't move, or it wins if thread B moved later. And thread A loses if thread B moved earlier. So by comparing these last two memory locations, A can determine whether it won or not. All right, and that's based on the ability to write two locations at once. Does anybody have a question about that? Okay, so our multi-consensus class is going to have this assign to object, which has 3 memory elements that are initially empty, and then a decide object. And well, let me step through it. So we're going to initialize 3 slots to empty. We're going to assign 0 or 1. We're going to assign 0 or 1 to the 2 entries. We're going to write our memory location there, change it from empty to 0 or from empty to 1. And then we're going to compute which is the other memory location. So that would be the memory location. That would be the memory location that we're not writing to. And then we're going to say if the other is empty or the other is ourselves, I mean, or if the other is or if the other location contains the other thread, then I win. Okay, and that will return the proposed value. Otherwise, I lose, and the other thread moved first, and I lose. Does anybody have a question about this? Okay, so the summary is, if a thread can assign atomically to 2 out of 3 array locations, then we can solve 2-thread consensus. Therefore, there is no wait-free multi-assignment from read-write registers. So what we're now going to consider is a new possibility. Up until now, we've only had read-write registers, but there's another option that we have open to us. Okay, and we're going to talk about that now. So we're going to consider read, modify, write objects. And the idea is we have a method call that returns an object's prior value x, and so it replaces x with mumble x, where mumble is just some function. We're going to make an abstract class RMW register, right? And it's going to have this get and mumble, the synchronized get and mumble value. And we're just putting synchronized on here because this has the semantics that we want, not because we're really going to have mutexes doing this. But anyway, it's going to say get and mumble. It's going to get the prior value. It's going to compute whatever it does and replace the value and then return the prior. So most synchronization instructions are RMW instructions, methods, and the rest can be trivially transformed into them. So here's a read operation. Okay, a read operation is just gonna find this. It's just gonna take this. It's gonna do nothing essentially, right? It's going to just leave the value unchanged. And then we're going to have a get and set operation, which is kind of like a write operation, and that's just going to overwrite the current value and replace it. Okay, and then there is the get an increment value, which is going to add 1 to whatever that value is. So this is something, at this point at least, this is something non-trivial. The last two are kind of trivial. This one is actually doing something. Likewise, get and add, right? We're just choosing A to be a different value than 1, or allowing for the possibility that A is a different value than 1. And then we're going to have compare and set. And compare and set is going to work like this. It's going to take two values. It's going to have an expected value. And what it's going to do is it's going to compare if the current value is the expected value. And if it is, it's going to return update, okay, and replace it. Then it will report true or false, which is a little bit different from the other register definitions, but it's just the way you can trivially make it work the other way. All right, so what we're going to do is we're going to characterize in our registers. We're going to characterize the f of x method, this mumble method. It's non-trivial if there exists a value such that v does not equal mumble v. So we're going to have some kind of change occurs. So identity is trivial and get an increment is non-trivial. Okay, any non-trivial RMW object has consensus number at least 2. And no wait-free implementation of RMW registers from atomic registers is going to exist. So hardware RMW instructions are not just a convenience, right? They're something truly meaningful. So subclasses of consensus have a proposed method which just stores x into proposed I, and then the decide method which determines the winning value, and it's customized and class specific. And so what we're going to do is we're going to implement our consensus object this way. We're going to have a decide method. We're going to propose our value, and then we're going to call r.getInMumble, and if it's equal to v, then we're going to return our proposed value, and otherwise we're going to return the other thread's proposed value. Okay, so I always do this. I always talk through the slide and then remember it's animated. But anyway, we initialize it. We initialize our register with v. Okay, and then we call our getInMumble to see if we're first. And then if we are, we return the proposed, and otherwise we return the other one's method. So we have displayed that a 2-thread consensus protocol using any non-trivial RMW object is possible. So are there any questions to this point? Let me just try and be a little more personal. Let's see, who do we have online? So, right, do you have any questions?
Nope.
Christopher, how about you?
Am I Christopher?
Christopher Clark.
Not really, but I mean, just to clarify, what's special here about the read, modify, write register is the fact that those get an increment and compare and set instructions are considered atomic, right?
Yes, they're going to be implemented in hardware. They're going to be machine level instructions.
But then each line of those instructions, right, despite it being implemented in hardware, right? So when those instructions are used, it's all happening all at once, right? It's not as if what we did with the read-write registers where you could read and operate on that value, but it wouldn't be atomic.
Right, these are atomic. So this is going to ensure that nothing can come between. There's no delay or anything else that can happen to cause this to fail or to cause this to get stuck. So these are special operations that just are going to be a read and a write, a read, a modify, and a write all rolled into one operation.
Right, yeah, it makes sense.
Okay, so what we're going to say is let f be a set of functions such that either for all fi and fj, either they commute or they overwrite. And the claim is that any set of RMW operations that commutes or overwrites has consensus number exactly 2. Okay, so test and set is going to overwrite, right? Or I'm sorry, yeah, get and set is going to overwrite. And get an increment or fetch an increment is going to commute, right? If I have 2 threads and they each call that, it's going to commute. So let's go back to our thinking about our critical state, right? And we're about to apply f of A or f of B. A applies f of A, B applies f of B, and C runs solo, and C's a 0. Or f of B applies f of B, A applies f of A, and C runs solo. And so C can't really tell, right, what happened first if they commute. So if I commute, right, the idea is if I apply f of A and f of B, then the result of those 2 operations, because they commute, it doesn't matter what order I put them in, and therefore C can't tell whether A or B move first, right? Does that make sense? All right, so now maybe the functions overwrite. And so A applies f of A and C runs solo, or B applies f of B and then A applies f of A and C runs solo. Now, B has to win, but the problem is that A overwrites. So C has no way to know that B moved, right? And so because these states look the same to C, it can't work out that B is supposed to win consensus. So there's a contradiction. So that means that we can only use consensus 2 with those methods. So many early machines provided these weak RMW instructions: the test and set, the fetch and add, and the swap. And we now understand their limitations, okay, and why we can't do that. So the compare and set, however, right, we have the expected value and the update value, right? And that's going to give us a consensus infinity object. So what's going to happen is we're going to take our atomic integer now, right, and initialize it with -1. And then we're going to compare and set that from -1 to our current ID, which, you know, could be thread ID.get. And then we're going to return the proposed value from r.get. So what we can do now, right, is with this compare and set operation, we can solve n-thread consensus, n-valued consensus for n threads. We use a single location in memory. Now you think about the locks that we made earlier in chapter 2. We made the Peterson lock, and we made the filter lock and the bakery lock, and all those things used a lot of memory, right? We needed extra elements in our arrays. We needed extra elements in our arrays for each thread that we wanted to include, right? But now we've got a method that can implement this sort of thing, and it can do it, you know, using one location in memory, and it can do it wait free. So realizing these kinds of things, these issues of about memory usage and wait free protocols led us over time to realize that the compare and set object was the thing we really needed. The compare and set instruction was the thing we really needed. The increment instruction doesn't really add anything. It's less powerful. And the get and set doesn't add anything. It's less powerful. And so at the end of the day, this is the only thing we need. And if you look at the source code for the atomic integer class in the Java virtual machine, you will find that all the atomic operations on that class are implemented with compare and set. There really is nothing else. Any questions? So the consensus hierarchy looks like this. We have read-write registers, which are one thread, and we have get and set and get and increment, which give us two-thread consensus. And then we have compare and set, which gives us infinity. We had multiple assignment. Now, before, what we did is we did a two-thread consensus model using a write to three memory locations. And so k equal 3 solved for 2 threads. This isn't the same as what this slide says, I'm now realizing. Assignment, well, okay, it's assigning to 2 out of 3 memory locations is what it's doing, right? Okay, so that's what's going on. So k assignment is going to be 2, is going to give us 2-thread consensus. All right, and what they're saying is if I have k equals 4, right, then I can have 6-thread consensus. And every consensus number has an object. And this can be extended to odd numbers. So using this multiple assignment, right, you can make 3 consensus and 4 consensus and 5 consensus objects. Does that make sense? I wanted, you know, it's nice to have something like this in here because you look at this counting that goes 1 to infinity and you'd just like to be able to see something in between. And this is something that, you know, if you had it, would go in between. Okay, so there is lock free and there is wait free. Who remembers the difference? Well, I mean, it's written right on the screen here. What's the difference between lock free and wait free?
Wait free just means that the processes are being utilized more efficiently, right?
Well, it means something more than that. You could have an inefficient wait-free implementation of something. What wait-free means is that all the processors finish in a finite number of steps. Okay, and it doesn't matter if one of them goes away or not. They all finish in a finite number of steps, no matter what. In lock freedom, okay, what we have is method. There's always some method that finishes, but any individual method could be delayed by the others, right? So I have two thread A and thread B are trying to do something. B wins, and then they try to do it again, and B wins, and they try to do it again, and B wins. And this is the sort of thing that's lock-free. And what the main difference is, if you look at a lock-free versus a wait-free code, is a lock-free code will generally have a while loop in it, and it's waiting for some condition to be true. Whereas a wait-free algorithm will not have a while loop. It will not be waiting for something because it's just going to do what it's going to do. And our compare and set implementation of the consensus algorithm, you'll notice, has no while loop in it. Does that make sense?
Yeah, so I guess just in a way to understand it better, like, do both of those go hand in hand in preventing deadlocks, or is one more relevant to deadlock prevention, or I guess, does that make sense?
So there's a table which I thought we showed, which was supposed to be shown in chapter 3, although I can't quite remember. It must have been. So there are 4 possibilities, right? So let's so let me draw some lines here. I'm just gonna make a little square up in the corner here. You have to forgive my horrible drawing because I have to use the trackpad. Okay. And Actually, wait, let me clear this. Let me see if I can't do. Oh, wow, I can draw a square. All right, I'm just going to draw it over top of things because it's just so ugly. I'm going to draw this. And okay, now I've got my table. And I'm going to say in here, does this look familiar to anybody?
Yeah, a little bit.
Okay, so and then we can say blocking. We can have non-block. All right. And then here we say all progress. And here we say one progress. So here we're going to say with a lock-free, lock-free is non-blocking. Okay, so nothing is going to block. Nobody's going to stop working. Okay, it might be sitting in a loop, constantly trying to do something. But the point of a non-blocking method is that if some thread just goes belly up and stops functioning, the lock-free method will succeed. It doesn't matter. Okay, if one of the threads gets lost, computation can still continue. However, it could be that if there's a bunch of threads, one of them doesn't make progress because the other ones are all busy doing things. Okay, in a wait-free, everybody is guaranteed to make progress. Everybody will finish in a finite number of steps. In a blocking method, we can make things deadlock-free so that you know, errors in code logic can't lead to the whole program just stopping. And then there's something beyond that where there's starvation-free, where we can guarantee that all the threads are going to make progress. Okay, you remember this table?
Mm-hmm.
Okay, so we're gonna probably see that again on tests, right? These are terms you're expected to know. Anyway, what's being said on this slide is that lock-free is often as hard to implement as wait-free, and sometimes you know which of these four things you wind up having is going to depend on what you're trying to do and what you need to do and what the best algorithms are for that case. All right. So again, wait-free, each method call takes a finite number of steps to finish, and in lock-free, infinitely often, some method call finishes. Okay, and so any wait-free implementation is also lock-free, and lock-free is the same as wait-free if the execution is finite. And they have this old saying, which is not particularly useful. It says lock-free is to wait-free, is deadlock-free, is to, I would say, starvation-free. Okay, so lock-free implementation consensus, as I said, is as impossible as wait-free consensus, or difficult as, whichever. And all the results we presented hold for lock-free algorithms also. So one of the things I want to point out is we are defining a consensus to include wait-free. Okay, we could have defined it to include lock-free, but it's just not how we did it. So consensus is universal. So from n-thread consensus, we can build wait-free, lock-free, linearizable, n-threaded implementation of any sequential sequentially specified object. And chapter 6 does this, and it does it in a really complicated way. But I think you can show it in a much simpler way. So consider this. I want to have my universal lock-free base class, right? And what it's going to do is it's going to have an atomic reference to an object, which represents a state, the state of whatever this object is. And then it's going to apply some kind of mutator to that state. And that mutator is going to look like, it's just going to have a compute method. It takes the old state and returns the new state. Okay, and so what I'm going to do is I'm going to have a while loop. And what I'm going to do is I'm going to get the old state, and then I'm going to compute a new state from the old state. And then I'm going to do a compare and set from the old state to the new state. And if I succeed, I'm going to break. Okay, now, because I have a while loop here, this cannot be, and while I keep trying to do something, so I have a while loop where I'm continuously trying to do something, that means I am not wait free. However, this is lock free because the only synchronization it's relying on is compare and set. And the problem with this way of doing things, right? I can make my universal lock-free objects and I can build everything on this. The problem is, if this compute operation is very expensive, right, then I might be wasting a lot of computation, because if threads are competing with each other, I might be throwing away computations a lot because the compare and set fails. Also, if there's global state somewhere, or if I want to print something during this compute method, right, then it's going to happen multiple times. I'm going to see things printed on the screen multiple times, or I'm going to update my global state multiple times. And when I discard the state, I might still have modified that global state. And so I might have created an inconsistency there. So there are circumstances, right, where using a universal lock-free object like this makes sense and is more efficient. And there are circumstances where it is less efficient. Does that make sense to people? Does anybody have a question about that? Okay, so I have some exercises assigned for this, and I will make a link for that. That takes us to the end of the lecture part of the discussion. And it takes us about an hour in. I can't believe that nobody has questions on this. So I'm just going to ask, before I try and launch into some other thing, I'm going to ask if anybody has any questions on the lecture or any homework or any of the other chapters or just anything from the course.
I think I kind of understand what you were going over today, but it's just kind of hard to come up with questions sometimes when it's so new,
Well, so a valid question can be, can you go over this again? I missed this point here. Can you go over, how can you go over again how writing to 2 locations out of 3 builds 2-thread consensus? I mean, sometimes, it's simply a question of going over some piece of it that didn't quite make sense, that almost made sense and didn't quite make sense.
You said we could ask questions about anything, right?
Yes, I do. Go ahead.
I don't think I fully understand the difference between what safe and regular. I think those are 2 terms that you used last lecture. Yes.
So safe, the difference between safe and regular is the following. So a safe register is safe because if the reads and writes to that register don't overlap, they're consistent. Okay. The problem is if they overlap, if a read and a write overlap, you can get any valid value for that register. So if it's an integer, right, and you have a write and a read, and your that register was initially 1, and you're writing it 2. Okay. While if that overlaps with a read, that read can come back with negative 15,000. Or it can come back with 666 or something like that. It can come back with anything because it's an integer and it's overlapping. All right.
All right.
Now, if we have a Boolean register that is safe, and I have and it's initially 0, and I'm writing a 0 in there again, and that overlaps with a read, it can return a 1, right? So the problem, so a safe register can return any valid value if it overlaps with, if the read overlaps with the write. Now, a regular register can only return either the old value or the new value if it overlaps. So if I have a Boolean register, a Boolean regular register, and I have a 0, and I'm writing a 0 in there, then, and it overlaps with a read, that read can only see a 0. Does that make sense?
Yep.
So, any other questions? All right, so what I thought I would do, this isn't completely worked out, and I know I have problems with it, but I thought, now that we've got all this machinery, right, we can build mutex, and in principle, we ought to be able to build condition variables. And as I say, I haven't completely worked this out, so I'm thinking that this might be a little joint debugging effort, and I thought that this might be valuable or it might not, but I thought it would be an experiment I wanted to try. So the idea is I have a mutex, and the way my mutex is going to work is I'm going to have a thread ID. I'm going to have an atomic integer, or the owner of the mutex. And what I'm going to do is I'm going to try to set that from, and you know what, this is stupid. I already see an error here. Yeah, -1. -1. This is probably what's wrong with it. All right, and the idea is I'm going to try to change it from -1 to my ID, right? And I have the thread yield in here, as you can see. So first of all, I was thinking about making this reentrant, but I decided that's too complicated. Take this part out. All right, and I have an unlock method, right, which is going to have, which is going to just set the thing to -1, and then I'm going to have a condition variable, and that condition variable, how would we make that work? Well, there's probably a billion ways to do it, but what I'm going to do is I'm going to have a linked list called a wait list, and whenever something wants to await, what it's going to do is it's going to push itself. It's going to, first of all, it's only going to, only want await to work if you have the lock. So await assumes that I am the owner of the lock, and so I'm just going to assert that. And then what I'm going to do is I'm going to push my ID onto this linked list of waiting values, and then I'm going to set, and I did have the same stupid error here. I bet this is all going to work now. Then I'm going to set the owner to -1, all right? And then I'm going to say that while the owner isn't me, I'm going to yield. All right, now for my signal method, what I'm going to do is I'm going to call lock, and then I'm going to go through the wait list. And if the wait list is of size 0, I'm going to just call unlock. So there's nobody to signal. That's what that means. But if there is something in the wait list, right, then I'm going to pop off this next value, and I'm just going to set that to be the owner. And I'm not going to call an unlock, because what I'm doing is I'm handing the execution over to that awaiting thread, right? So it's going to resume its lock. And I'm making sure that all access to the wait list, all modifications on reads on the wait list are covered by this lock, okay? And then for signal all, what I'm going to do is I'm going to count the number of things in the wait list, and I signal that many times, okay? And what's going to happen with that is each time I signal, it's going to pop one thing off the list. So anything that was on the list at the time I called signal all will get popped off. So that's my implementation of condition variables. Does this make sense to people?
Yeah.
Okay, then I have a queue class, and I'm going to try to use it the same way that I would use it from other things. So I have my array of items. I have my head and tail. I have my enqueue method, which says that while the queue is full, I'm going to wait, and then once it isn't full, I'm going to stick something on there, and then I'm going to signal the signal the empty to unlock. I'm going to signal for empty, and then I'm going to have, while the thing is waiting on empty, I'm going to do nothing, and then it's going to return the next item in this queue, and then it will call on the full signal. So it's this logic should all look familiar. And then what I have is I have a queue, which is going to be of size 3, and I have 10 threads. I'm just going to have either even numbered threads are going to dequeue and odd threads are going to enqueue, and everything should all balance at the end of the day. Yeah, and it's working now because I, like a silly person, I put 0 when the thread IDs could start with 0. Okay, so this shows you. So this was a less exciting debugging session than it might have been, but it shows you how you can implement mutexes and condition variables using atomic integers. Now we could try, if we wanted to be fancier, we could figure out how to make this work with, reentrant locks. We could have a reentrant version of this mutex where we had a hold count, and we'd have to have some other logic for the condition variable then. And then there's other things about the condition variable. So this condition variable assumes that this condition variable assumes that when I signal, I do not have the lock. So I had to be careful to call it that way. And in fact, I should probably put an assert here, right? I should say m.owner get equal -1. All right. And the problem is that calling signal might block because I have this lock method here, and that is not as efficient as it might be. So if I worked harder, maybe I could come up with another implementation of signal that didn't involve blocking. But this was just the first thing that occurred to me as a way to build this. And as you go in, when you go into this queue, you notice that I always call it after the unlock method, right? So, any thoughts? All right. Well, okay. Those of you who asked questions during this lecture, great. Those of you who did not, please remember to ask a question during office hours. All right?
Sounds good.
All right. I will see you all later.